Welcome to today's lecture. A couple of days ago we started a series on radioactivity. We have looked at natural radioactivity and artificial radioactivity. Don't forget, we said that artificial radioactivity is also referred to as artificial transmutation. By now, we should be able to tell the differences between natural radioactivity and artificial radioactivity. Let me help you out in case you may not be able. For natural radioactivity, disintegration of the nucleus is spontaneous. For artificial radioactivity, disintegration of the nucleus is forced by bombarding the nucleus with fast-moving particles. Number 2, for natural radioactivity, the nucleus is unstable. For artificial radioactivity, the nucleus is stable. Number 3, for natural radioactivity, the nucleus is always heavy. For artificial radioactivity, the nucleus is light. Today we'll be looking at binding energy. Binding energy. As you can see, binding energy is the energy released when a nucleus is formed from its constituents. The constituents of a nucleus are protons and neutrons. This is supposed to be neutrons, please. Neutrons. Okay, so and its constituent. Don't forget the constituent of the nucleus are protons and neutrons. We can define binding energy also as the energy required to completely separate a nucleus into its individual protons and neutrons. Now, the protons and neutrons are called nucleons. So please, I want you to take note of that. We may eventually use that word as we go on in the lecture. So protons and neutrons are called nucleons. Importance of binding energy. Number 1, it shows how stable a nucleus is. Number 2, the greater the binding energy, the more stable the nucleus. Number 3, nuclear reactions such as fusion and fission depend on binding energy. This will take us to mass defect. Mass defect. When the nucleons, that is, protons and neutrons, combine to form a nucleus, the mass of the nucleus is less than the total mass of the free nucleons. Don't forget nucleons. The nucleons are the protons and neutrons found in the nucleus of an atom. So what are we trying to say here? That if it were possible to separate the protons and neutrons from the nucleus, and we find the mass of the individual constituent, that is the mass of the protons and the mass of the neutrons, and then we add the mass together, it is discovered that the total mass of the protons and neutron is greater than the mass of the nucleus itself. So that's exactly what I'm trying to say here. When the nucleons, that is protons and neutrons, combine to form a nucleus, the mass of the nucleus is less than the total mass of the free nucleons. So the mass defect is the difference between the total mass of the free nucleons and the mass of the nucleus. Don't forget, we've ascertained that the total mass of the free nucleons is greater than the mass of the nucleus. So if you find the difference is what is referred to as mass defect. So mass defect then is mass of proton plus neutrons minus mass of the nucleus. So let's see an example. Calculate the binding energy of sodium. We're given the nucleon number to be 23 and the proton number to be 11. We're given that one proton is 1.0078 atomic mass unit and one neutron as 1.0087 atomic mass unit. Don't forget that we have 11 protons. This is the proton number. Proton number is the number of protons in the nucleus of an atom. So 11 here is the proton number, which tells us the number of protons. This is the nucleon number, or what we call mass number. The mass number is the sum of the number of protons and neutrons in the nucleus of the atom. So if you subtract 11 from 23, that will give you 12. So have 12 neutrons. So 23 minus 11, that gives 12. So 12 neutrons. So 1.0087 atomic mass unit times 12 will give us this value. If you multiply this, that is the one proton, by 11, that will give us this. If you add up, that will give us 23.1902 atomic mass unit. U, as used here, it refers to unified atomic mass or atomic mass unit. So then our binding energy is 23.1902. That is what we got here, the total mass of the free protons and neutrons minus the mass of the nucleus, which is 23. So 23, that will give you 0.192 unified atomic mass. One unified atomic mass, or one atomic mass unit, is 931 mega electron volt. The word mega there, electron volt, the mega there is 10 raised to the power 6, then electron volt. Mega is 10 raised to the power 6 electron volt. 1 electron volt is 1.6 times 10 raised to the power minus 19 joules. So one unified atomic mass, or one atomic mass unit, is 931 times 10 raised to the power 6 times 1.6 times 10 raised to the power minus 19 joules. So converting 0.1902 unified atomic mass to joule, we'll say 0.1902 unified atomic mass is 0.1902 times 931 mega electron volt, since one unified atomic mass is 931 mega electron volt. So we convert the mega electron volt to joule. Of course, don't forget mega, M, capital letter M is 10 raised to the power 6 electron volt. And so then 1 electron volt is 1.6 times 10 raised to the power minus 19. If we resolve everything, we'll get 2.8332 times 10 raised to the power minus 11 joules. Uses of radioisotope or radiation. Here we're going to be looking at the medical use or uses and industrial use or uses. Remember we said uses of radioisotope or radiation, gamma rays. Don't forget, gamma rays are not radioisotope. They are radiation that emanate from the nucleus of a radioactive element. Radioisotopes are unstable isotopes of elements that decay spontaneously by emitting radiation in order to become more stable. So gamma ray are not radioisotopes, but they fall under radiation. So since we're looking at uses of radioisotope or radiation, gamma rays are used to destroy cancerous growth. Number 2, cobalt-60 is used for the treatment of cancer. Number 3, iodine-131 is used for the treatment of cancer of the thyroid gland. Number 4, phosphorus-32 is used for the treatment of the cancer of the blood, otherwise called leukemia. Number 5, gamma rays are used to sterilize medical equipment. This will take us to the industrial uses. For industrial uses, we have number 1, gamma rays are used to monitor and control the thickness of sheet materials. Number 2, gamma rays are also used to control the filling of packets, tins, tanks, or machine. Number 3, cobalt-60 is widely used in industrial radiography for the rapid checking of faults in welds and casting. This will take us to theory of relativity. The theory of relativity was proposed by a renowned scientist called Albert Einstein. According to Albert Einstein, mass and energy are interconvertible. That is, mass can be converted into energy, and energy can be converted into mass. This relationship, or the relationship between mass and energy, is depicted in the Einstein's equation. That is, E is mc squared, where E is energy in joules, m is mass in kilogram. That mass sometimes can be taken as mass defect, which is m1 minus m2. Ordinarily, change in mass should be m2 minus m1. But because disintegration involves moving from a large mass to a smaller mass, so our defect will be m1 minus m2, because the initial mass is always greater than the final mass after disintegration. C is speed of electromagnetic radiation, and it has a constant value of 3 times 10 to the power 8 meter per second. The equation shows that a small amount of mass can produce a large amount of energy, because c squared is extremely large. This is part 10. I will see you in part 11.